In a previous video, you might have learned of a very useful technique for um, solving trig expressions, and that's SOHCAHTOA. We'll remind ourselves about that in just a second. This is definitely a very handy tool to help us remember how to find sine, cosine, and tangent when working within a right triangle. Um, a more mathematical definition and a very important definition that we'll use multiple times in the course is the point definition for our trig functions. Remember, SOHCAHTOA talks about, okay, if you're in a right triangle and you're standing at some angle, then you have now established a side opposite that angle, a side adjacent to that angle, and the hypotenuse of that triangle. And SOHCAHTOA helps us remember which sides to divide when we're evaluating a particular trig function. However, what if we're asked to find sine, cosine, or tangent just given a single data point? Or maybe we're given a data point that would be troublesome to dig our way out of with SOHCAHTOA. I'll show you that in a second too. So we want to make sure we know the point definition because again, this is used in various places in the course. We'll see it again in chapter 6. So given some point here, one thing we'll learn in trig is that there's really two ways to get here. Traditionally, algebra tells us to walk left or right and up or down, right, to get to our point. So we would walk right X and up Y to get to this data point I've drawn here. Trig lets us take another look at it too, and it says you can also imagine just some angle that you would have to rotate through and some distance you would have to walk to get there. Okay, and so if I want to describe that point, I've got a couple ways to do it, and our trig functions relate these numbers together, the x and the y and the r and the theta. So the point definition of trig functions are this. To find cosine of angle theta, if you know some point, it could be any point on the terminal side of that angle theta, right? It could be there, it could be way up here, it doesn't matter. But what you do is you take the x value of that point and divide it by r, the distance from the origin to that point. To find the sine function, sine of theta, you take the y value of your data point and again divide it by r, which is the distance from the origin to wherever that point is on the terminal side of angle theta. To get tangent of angle theta, we would take the y value over the x value of the point. So it's not dependent on r. And because we have our reciprocal identities, we know that if I were looking for secant of theta, I just need to flip over the cosine values. It would be r over x. Since cosecant is the reciprocal of sine, cosecant of theta would be r over y. And then cotangent of theta, the reciprocal of tangent, would be x over y. This definition is handy for a variety of reasons. Like I've mentioned before, we're going to come back to it and use it in different ways. But for one, it can kind of easily point out when trig functions might be undefined. So for example, I'm looking at like the tangent function here. Okay, and I see that it's got x in the denominator. So because I see the x value in the denominator, I know that if I'm looking for tangent of any angle that lives on the on the y-axis, right? Any point on here would have an x value of 0, right? And some y. Even down here, we would have an x value of 0, and then there would just be some negative y value down here. But if I wanted tangent of any of these angles here, right, I would pick a point on the terminal side of that angle. Well, that x value is going to be 0, tangent's undefined there. This is all stuff we're going to explore a little bit more in the course, but again, that's one plus side of the point definition. The point definition also lends itself well to SOHCAHTOA. I mean, SOHCAHTOA is just really an abbreviated way to remember this more mathematical definition. Because if you look back at your diagram here we drew, I could make a right triangle out of this. I could just add these two side lengths here. And so now I've got a right triangle established. Again, I'm standing at angle theta. So the side that's opposite angle theta is actually a length of y. And the side that is adjacent to angle theta has a length of x, right? Since those two side lengths got me to the point xy. And so I could see that if I wanted cosine of theta, SOHCAHTOA would say take the adjacent and divide it by the hypotenuse. So in this diagram, the adjacent has length x, hypotenuse has length r, and so it's the same thing. To kind of go back to that example I did earlier, though, to show where SOHCAHTOA might break down, let's again look at a 90-degree angle here. So let's look at a 90-degree angle, and I just pick some point on the terminal side of that angle. For an angle that's quadrantal, right? A quadrantal angle is any angle whose terminal side lies on one of the axes, either the positive or negative xy axes. I cannot construct a right triangle here to use SOHCAHTOA, right? If I had some angle out this way, no problem. I could just pick a point on the terminal side, make my right triangle, and I could use either the point definition or SOHCAHTOA, whatever you prefer. But when you've got an angle that's quadrantal, I can't construct a right triangle out of it. Remember, the point that lies on the terminal side of your angle, that distance is r, right? That's kind of like representing the hypotenuse of the right triangle you're drawing. And so if my hypotenuse is straight up here, I can't construct a right triangle. I've got no left or right to draw to it. So for quadrantal angles, SOHCAHTOA does not help us out at all. It does really well if we're looking at a right triangle or we can construct a right triangle. SOHCAHTOA is a great way to remember the trig expressions. But a more mathematical definition, again, that we will use repeatedly is the point definition.